So here we have a problem where there's a collision. So you should be expecting law of conservation of momentum. And then we have a simple harmonic motion type problem, which is what is the amplitude after the collision. Now, this is definitely what I would call a ballistic pendulum type problem. And so we have three really important locations here. A is before the collision. We got to keep these straight, otherwise you can get into trouble. B is immediately after the bullet comes to rest relative to the block, but before the spring compresses significantly. That's a tricky one. I'm going to come back to that. C is, let's say, at the full compression of the spring, which is kind of what we're looking for, the amplitude, the full compression of the spring. So back to B. This is one of the tricky things about this type of problem that you might not pick up on as a beginning student. But the only way to solve this is to assume that the collision takes place so quickly, that the bullet comes to a stop within the block so quickly that there really hasn't had any time. There hasn't been any time for the spring to start to compress. And so that allows us to sort of separate what's happening from A to B versus what's happening from B to C. And what's happening from A to B is a collision. So here I'm going to use the law of conservation of momentum. But then what happens from B to C is you have a spring exerting an external force. I should go back and remind you that you can use the law of conservation of momentum whenever there is no net external force on the group of objects that you're looking at. So we're looking at the bullet and the block, and when they collide with each other, they're just exerting a force on each other. That's an internal force. Now there's the possibility of the spring exerting an external force, but that's why we're assuming that the spring hasn't had any chance to significantly compress by the time the collision is over. So that sort of eliminates the external force between A and B, and so we can use law of conservation of momentum. Now, once that spring starts to compress, that is going to change the momentum of the system, and we can't use that anymore. However, since it's a spring, and since springs are conservative forces, we can very easily use UCWUC, the law of conservation of energy. By the way, the reason we can't use UCWUC between A and B is because when the bullet hits the block, they exert a force on each other that is definitely a non-conservative force. It generates a lot of heat, a lot of damage, and we just don't know anything about that. We don't know enough to be able to calculate that W in that equation, so it makes it impossible to use. Okay, anyway, back to finding the speed of the bullet and the block combination right after the collision. So I'm going to take a look at all of the momentum at A, and it has to be equal to all of the momentum at B. Well, at A, the only thing that has momentum is the block, mv. That's it. Afterwards, the two objects are stuck together, moving with the same velocity. So you have these two masses, little m and big M, and their mutual final velocity. So the answer here is simply mv divided by m plus m. And that is the answer to the first part of this question. Second part of the question is, what is the amplitude of the simple harmonic motion? Amplitude is the maximum compression. And so that's going to be the point where all of the energy is in the form of elastic potential energy. And so, I was thinking there's more than one way to solve this. Let me do it the traditional way by saying that the potential at B plus the kinetic at B plus the work is equal to the potential at C plus the kinetic at C. And remember, I would never do U at A plus K at A, because between A and B, there's this huge amount of non-conservative force that takes away a lot of this energy here. And we don't have enough information to calculate that. So I'm just going to go between B and C, where there's only a spring, so there is no non-conservative force. And B is just before the spring compresses, so there's no potential energy. And so we're just going to have 1/2 mv squared at location B. And then over here at location C, we have 1/2 kx squared. And for a moment it comes to a stop. And you might remember earlier I said, hey, there's another way to solve this. The other way to solve this is if you just happen to remember that for a simple harmonic oscillator, 1/2 mv max squared is equal to 1/2 k x max squared. And that's really what we have here. Certainly, full compression is the maximum x that you're going to get in this situation. And the moment just after the collision, when the spring is totally still relaxed, by definition, that's equilibrium. And that's the location where velocity is at a maximum. So either way, you end up with the same conclusion. Looks like the halves are going to cancel out here. I need to substitute in the previous value for that maximum velocity. And by the way, this m, I'm being a little uncareful here. This m is actually those two masses because this is the moment after the collision. And so the two masses are stuck together. So that's what this mass is. That maximum velocity is the mass that I just is the velocity I just calculated. So that's mv over m plus m. And that quantity has to get squared. And then on the other side of the equation, I believe we're allowed to use k in this. Yes, k is one of the given variables. And we're trying to solve for x max. And so the rest of this is really just algebra, but let me give it a quick whirl. So m plus m is going to cancel out one of the m plus m's here because of the square. So let's see what that looks like now. So we're going to have mv quantity squared divided by m plus m, and the k comes over to the other side on the bottom as well. So that equals x squared, and then I just need to take the square root of that. And so maybe simplifying that, we would get mv times the quantity square root of mv over m plus m times k. And that should give us our x that we're looking for.